So we talked about simple harmonic motion by thinking about oscillatory motion of a mass on a spring, moving up and down, up and down. But we can also have simple harmonic motion with a pendulum. So you put a mass at the end of a long string, you tie that string to some immovable point, and you let that mass swing from side to side. So here I've got a pendulum. I've got a string connected to, let's say, the ceiling, and I've got a mass attached to it. Straight down from where my mass, or where my string is attached to the ceiling, that's my equilibrium point. And then what's going to happen is that I'm going to pull my mass off to some side, and then my mass is going to swing through the equilibrium position here. It's going to swing over to the other side, and then it's going to swing back through the equilibrium position, and then it's going to swing back again to the place where it started. So for our pendulum, that would be one complete oscillation, starting from point 1, moving through equilibrium at point 2, getting to its maximum amplitude on the other side at point 3, swinging back through equilibrium at point 4, and then coming back to where it started again, coming back to point 1. That would be one complete oscillation for your pendulum. Okay, and you can also think about the period or frequency of oscillation for the simple pendulum. So the frequency of oscillation for your simple pendulum is 1 over 2 pi times the square root of the surface gravity, which will be 9.8 meters per second squared for us, divided by the length of your strings. This would be the length of my string, or the length of my pendulum, okay? And the period is 1 over the frequency. So 1 over the frequency is equal to the period, okay? So if I wanted to find the period of oscillation, which is essentially the time it takes my mass to go from point 1 to point 3 and back to point 1 again, that's the period for one oscillation. That period is the inverse of my equation for frequency. So then the inverse of this is equal to 2 pi times the square root of L over G. So that would be your period of oscillation for here, my simple pendulum. So I'm going to walk through the final problem in the pre-lab with you, and that's about using a pendulum on another planet. Astronauts in another galaxy perform an experiment on a planet to determine the planet's surface gravity G, because the equation for the frequency of a simple pendulum is dependent only on G and the length of that pendulum. They construct a simple pendulum by suspending a mass of 200 grams, or 0.2 kilograms, from a 0.8 meter long string. When the mass is pulled to one side and let go, the mass executes simple harmonic motion. The mass completes 10 oscillations in 20 seconds. What is the surface gravity on this planet? G equals question mark. Okay, so the first thing I can do is I can get the frequency of oscillation right off the bat. The frequency of oscillation is your number of oscillations divided by the time it took you to make all those oscillations. So the frequency of oscillation here for the simple pendulum is 10 divided by 20 seconds. And so 10 divided by 20, that's 1/2, that's 0.5. So my frequency of oscillations is 0.5 hertz, because the unit of frequency is inverse seconds, which we call hertz. So now I know F, and I know that F is equal to 1 over 2 pi square root of G over L. Okay, so I need to solve this equation for G. That's what I'm looking for. So what I'll do is I'll multiply both sides by 2 pi. So I multiply both sides by 2 pi, that cancels the 2 pi on the right. And so then I'll have 2 pi times the frequency equals the square root of G over L. Now to get rid of that square root, I can square both sides. So let's square both sides. Okay, so then this becomes 2 pi frequency squared equals G over L. And now I just need to solve for G. So G is equal to the length of my pendulum times 2 pi frequency squared. And so with these quantities that I'm given here, I find that the acceleration due to gravity, or the surface gravity on this planet, is 7.89 meters per second squared. So just a little bit smaller than the 9.8 meters per second squared that we have on our planet. And so before we leave, let's compare the equations for the frequency of oscillation for our spring simple harmonic oscillator and for our string pendulum. They both execute simple harmonic motion. So the frequency of oscillation for our spring simple harmonic motion is 1 over 2 pi square root of k over m. And our frequency of oscillation for the pendulum is 1 over 2 pi square root of g over L, okay? So for our springs simple harmonic motion, the frequency is solely dependent on the spring constant and the mass that's attached to the spring. So for the string pendulum, when we're thinking about simple harmonic motion in the pendulum system, the mass doesn't actually play a role in the frequency. It's just the length and the surface gravity. You'll find in these experiments that the amplitude of the oscillation does not impact the frequency. So no matter how far you pull your simple pendulum away from equilibrium, or your spring simple harmonic oscillator away from equilibrium, that amplitude is not going to have an impact on the frequency. You should find that anyway.